Hello and welcome to today's lesson. So in today's lesson, we are going to look at chemical bonding using the Lewis structures. So chemical bonding is just the joining of atoms, obviously chemically. Now we have two types of bonding. In this case, we're going to look at covalent, or we can look at ionic bonding. Obviously, we know that we have metallic, we have hydrogen bonding, and so on and so forth. Now, for now, I want us to focus on how to demonstrate chemical bonding using the Lewis structure. So, demonstrating chemical bonding using the Lewis structure. So for us to demonstrate this type of bonding, obviously we have to pay attention to the valency electrons. So valence electrons are just electrons in the outermost shell. Or these are electrons that take part in a chemical reaction. So if we go back to the periodic table, and we try to highlight the valence electrons in hydrogen, we're going to have that. In helium, we're going to have 2 electrons. When we go to lithium, we have 1. Potassium or sodium, we have 1. Potassium, we have 1. So all those in group 1 will have 1. When we go to beryllium, we have 2. Calcium, we have 2 valence electrons. Magnesium, it's the same thing, we have 2. If we look at boron, we have 3. Aluminium, it's the same thing, we're going to have 3 valence electrons. Those are electrons in the last shell. Carbon, we have 4. Silicon is the same thing, we're going to have 4. Nitrogen will have 5. Then oxygen will have 6. Fluorine will have 7. And neon will have 8. Phosphorus will have 5. Sulfur will have 6. So this is just the Lewis structure of these particular atoms. We are just interested in the electrons in the outermost shell. Obviously, we understand that helium is part of the group 8 or group O. It's part of the noble gases. Now, for us to demonstrate what we call chemical bonding using the Lewis structure, we have to understand the following steps. So the steps to write the Lewis structure. So the steps are as follows. So step number 1, hydrogen is always a peripheral. Element when we are dealing with a Lewis structure. So a peripheral, I will give more context to this. when we're dealing with an ox acid, hydrogen is attracted to oxygen. So in a case where there is an ox acid, there will be this bonding. So hydrogen will be bonded to oxygen, and you can see the demonstration there. 3, generally less electronegative atoms are central atoms. So usually if this is a less electronegative atom, then it's going to be bonded somewhere in the middle. You put them at the center. Then 4, generally more electronegative atoms are peripheral, meaning they occupy the sides. So in this case, they'll be put on the sides. So these are peripheral atoms. Rule number 5. In a case of sum total number of outermost electrons, in a case when we're doing the total number of electrons, which are the valence electrons, in a given target atom X, there are 2 conditions. So if you are dealing with a positively charged compound, I will give more examples. If you're dealing with a positively charged compound, we subtract. Then B, if we are dealing with a negatively charged compound, we add to the sum. Allow me to look at the we look at the 6th rule. Then we're going to see how these rules or steps apply. When connecting atoms, at least we use a single bond. So if I'm connecting A to B, a pair will mean that A is a single bond. So at least I use a single bond to connect. Then 7, what happens to the remaining when we do the total, when we have the remaining electrons? So the remaining electrons are distributed to peripheral atoms as lone pairs to complete either the duplet or octet rule. I will give more emphasis on what some of these rules imply. Then rule number 8, if still some electrons remain, what we have to do is we assign them to the central atom. So in a case where we have distributed those electrons and then we have extra electrons, then we can distribute them to the central atom. Number 9, sometimes double, which is double, and triple bonds are created. We will talk about resonance. Are created to complete the octet. To complete the octet rule using lone pair electrons. Let's quickly look at the examples and we apply these rules. So demonstrate chemical bonding in the following using a Lewis structure. Okay, so say example number 1, we are given H2O. So to demonstrate the bonding in this compound, the first thing we have to do is we have to calculate the sum of valence electrons. So we have to know the number of electrons total that are taking part in a chemical reaction. So we'll split hydrogen, we have 2, then the valence number for those is 1, so we have 2. Then oxygen, we have 1, then the valence number, so this is the valence electron, sorry. Valence electron for oxygen is 6. If we go back to what I gave here, so the valence electron here is 6. So this will give us 6. So we add this together, it's a neutral compound. This gives us 8. So how do we distribute? According to the rules, so oxygen will be in the middle, then we'll have hydrogen, and we have hydrogen. We said hydrogen exists as peripheral compounds, you put them in the sides. Then we distribute at least a single bond. So a single bond is represented by a pair of electrons. So we'll put 1, 2, 3, 4. So when I subtract from there, I will remain with 4 electrons. Then those 4 remaining electrons will be put as lone pairs on oxygen. So when we look at this, which can also be represented as this, we'll realize that the oxygen is stable because it satisfies the octet, and then the hydrogen there is stable because it satisfies what we call the duplet rule. Let's look at another example. B, we demonstrate for NH3. So we have to know the sum total of valence electrons. So nitrogen, we have 1. The valence electrons for nitrogen is 5. This gives us 5. Then hydrogen, we have 3. The valence electron is 1. which gives us 3. When we add the 2, we get 8. So nitrogen goes in the center, then hydrogen, hydrogen, hydrogen. So the next thing is at least we distribute a single bond or a pair of electrons. So 1, 2, 3, 4, 5, 6. So when we subtract 6 there, we remain with 2. So the 2 will be distributed on the central atom. This can be written as this. And then we have a lone pair there. Let's look at another example. C, in a case where we're given NF3. So the sum of valence electrons, nitrogen will be 1 by 5, giving us 5. Fluorine will be 1 by 3, so we have 3 by 7, giving us 21. The total will give us 26 valence electrons. So nitrogen in the middle, fluorine, fluorine, fluorine. So we distribute 2 electrons, 2 electrons, 2 electrons. So we have subtracted 6 to remain with 20. So for fluorine to be stable, it has to satisfy the octet. So we're going to distribute, that is 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We subtract 18, you remain with 2. So the 2 will be put there as lone pairs. So this also can be written like this, and then we distribute. So the whole purpose of undergoing chemical bonding is for these respective atoms to become stable. So by stable, it means it's either you satisfy the octet, that is 8 electrons in the last shell, or you satisfy what we call the duplet, which is 2 electrons in the outermost shell. Let's look at another complex example. So started with 1, this should be 2, this should be 3, then 4. We are given sulfuric acid. So this one is a bit more interesting in terms of the total of hydrogen. So there's 2 times 1 giving us 2. Sulfur, there's 1, the valence electron is 6, that is 6. Then oxygen is 4, the valency is 6, giving us 24. So the total is 32 valence electrons taking part in the chemical bonding. So in this case, we have sulfur, then remember we have oxygen, 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 then the hydrogens will always come as peripheral. Remember, in the oxyl acid, it's at this bond, hydrogen is always bonded to oxygen. So we count the number of electrons that we have distributed so far. So 2, 2, 4, 6, 8, 10, 12. So now we have to satisfy the octet. So for this to satisfy the octet, you're going to put 2 more. So if we count 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, then we have to count the number of electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So we realize that we have distributed all the electrons. And this can equally be written as this. O, there's this, then okay, then those can satisfy the octet. So that is sulfuric acid. Let's look at another example. This was example 4. Let's look at example 5. In a case where we are given COCl2, so there's carbon, which is 1 by 4, giving us 4. There's oxygen, which is 1 by 6, giving us 6. There is chlorine, which is 2 by 7, giving us 14. So the total here is 24 valency electrons. So how do we distribute these? So carbon goes in the middle, then we have oxygen this side, we have chlorine this side, we have another chlorine here. So we have used 6 electrons. When we subtract 6, we remain with 18. So that 18, we use them to satisfy the octet. So 6, 6, 6, 6, 6, 6. So in this case now, it becomes more interesting. So here you realize that this has got 8 electrons, 8 electrons, 8 electrons, satisfying the octet. But the carbon in the middle has got 6 electrons. So this is quite unstable for carbon, for this particular carbon. So for the carbon to become stable, we do what we call a resonance. A resonance is where a compound has got more than one structure. So what we do here in this case is a lone pair will move and go there. So now what we're going to have is a carbon with, so a pair of 4 electrons there, then oxygen with 2, 2, then we have a pair here, carbon, which is chlorine, this, and a pair chlorine. So what this simply means is we have this, the double bonds there, carbon, single bond, chlorine, another chlorine, single bond, then we complete the octet. So all these are neutral compounds. All these are neutral compounds. Let's look at a case where we are given charged species. So Lewis structure of charged compounds, or charged species. For example, we are given H3O+. So how do we go about it? So we find the sum of valence electrons. So hydrogen there is 3 by 1, giving us 3. Then oxygen there is 1 by 6, giving us 6. The total gives us 9. But remember, this is a positively charged. So according to the rules, when we have a positive, it means there is losing of an electron. So here we subtract 1, and the total number of electrons will be 8. So to demonstrate this, we'll have oxygen, hydrogen, 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 then a pair of electrons there, a pair of electrons, a pair of electrons. So we have used 6. We have 2 remainder that we put there as lone pairs, which can equally be represented as H, O, H, H, lone pair, then enclosed, and we put a positive. Let's look at one last example where we are given another charged compound like CO3 2 negative. So we find the sum of valence electrons, which is going to be carbon 1 by 4 giving us 4, then oxygen 3 by 6 giving us 18, and in this case the total is going to be 22. But now here the charge is negative, meaning it's gaining 2 electrons. So we add 2 electrons to get the total of 24 valence electrons. So how do we distribute? So we have a carbon, we have oxygen, we have oxygen, we have oxygen. So we put 2, 2, 2, 2. So we have used 6. We subtract 6 to remain with 18. So the 18 will occupy the oxygens to satisfy the octet rule. So we have something like this. Now, when you look at this particular compound, you will realize that the carbon only has 6 electrons, meaning it's unstable. It's unstable. So for this carbon to become stable, we have to do a resonance where a pair of electrons is taken there. And this becomes this double bond, oxygen with 2 pair of electrons, carbon, oxygen, oxygen, then this, a pair of 2 electrons. And then when we calculate what we call the formal charge, this will have a negative, that will have a negative. Or if you want to just enclose this, and that's the structure that we're going to have. All right, see you in the next video.